Hi, today we're going to revisit a 105 concept, energy. You guys know from 105 that there are lots of different types of energy. There's kinetic energy, potential energy, chemical energy, thermal energy. And it's one of the most hallowed and sacred principles of physics that energy cannot be created or destroyed. It can only sort of change from one form to another. For example, when you hit the accelerator in your car, you're changing the chemical energy stored in the fuel to kinetic energy of your vehicle. When you push the brakes, you're transferring all that kinetic energy into thermal energy as you heat the brake pads. And there were a couple of, one of the other types of energy that you talked about was potential energy, which is related not to the motion of the particle, that's kinetic energy, 1/2 mv squared. Rather, it's related to the position of the particle, right? It's something like stored energy. You talked about gravitational potential energy, talked about spring potential energy, right? If something has a lot of gravitational potential energy, it's way up high, right? Because if you were to drop it, it would then pick up kinetic energy as it falls, right? So potential to kinetic. So it's kind of a form of stored energy. Anyway, those are all Physics 1 principles. But it turns out that they have a lot of application in the world of electricity as well. So we're going to talk about electric potential energy and electric potential. Now, it may seem like I've just said the same thing twice, electric potential energy and electric potential, but it turns out these are two actually very different things. And I'll come back to that. In fact, the symbol we use for electric potential energy is capital U. The symbol we use for electric potential is capital V. So we're going to figure out what I mean by that today. But before I actually talk about these forms of potential and potential energy, I want to revisit an old form, the one that you talked about a lot in 105, which was gravitational potential energy. If you have a box, and it has some mass, call it m, and you have it lifted a certain height, h, above the ground, and then you allow that object to descend through that vertical distance h. Here's the ground. Okay. Call this position A, call this position B. So initial position is A and final position is B as the block goes through this descent. An interesting thing to talk about in this scenario is work. You remember work is a physics concept that's very closely related to energy. In particular, we can talk about the work done on an object by a particular force. And in this case, as the object descends, right, if you were to sort of sketch a free body object or free body diagram of the object as it descends through this vertical distance, if you drop it from position A, the only force acting on this block as it descends is the gravitational force. Call it F sub g, which you guys remember is equal to mg. And so the question I have then is how much work does the gravitational force do on the block as it descends through this distance? So the work done by gravity. I'll call that W sub g, right? That's going to be, if you remember the definition of work, it's a force times a displacement times the cosine of the angle between the two vectors, the force vector and the displacement. But in this context, the F would be F sub g, the gravitational force. The displacement would be h. And now we have to think about the angle between those two vectors, F sub g and h. Well, F sub g is down and h is down, so the angle between those two things is 0, right? So cosine of 0 degrees, as you guys know, is 1. And so it's just F sub g times h. F sub g, as we know, we've already said is mg, so that's just m times g times h. So the work done by gravity as it descends through this vertical displacement is mgh. Now that should ring a bell, right? That should remind you of the old potential energy formula for gravity. In particular, if we define gravitational potential energy, U sub g, if we define that to be m sub g, or mgh, then we can say that the work done by gravity is going to be the negative of the change in the gravitational potential energy, right? This is how U sub g is actually defined. Now, in this case, as it goes from position A to position B, right, final potential energy minus initial potential energy, that's delta U, would actually then be a negative number. So it would be like 0 minus mgh. And so that's a minus mgh, which gives you positive mgh right here, right? So that's why we have to have a minus sign in order to make this work. But this was our definition for potential energy. By the way, this process could certainly happen in reverse. I could take the object from the ground, called position B now, initial position, and move it up. In that situation, the work done by gravity would be negative mgh. Why? Because in that case, the displacement would have been up, and the force would have been down, so that would be a cosine of 180 degrees. So this angle, phi, that shows up in this formula, definitely is definitely an important thing. One other thing, actually, it doesn't even matter. It turns out that because gravity is a conservative force, it doesn't even matter how I go from position A to B. I could take a weird convoluted path from A to B, and the work done by gravity is still going to be mgh. That's what made it incredibly useful, this idea of potential energy, for solving complicated trajectories like roller coasters and other things like that. This is gravitational potential energy. What about electric potential energy? Well, you guys have already seen that there's a lot of similarity between the electric force, aka Coulomb's law, and gravitational force, Newton's universal law of gravitation, or Newton's law of universal gravitation. Let's imagine that in some region of space, I have an electric field that points down. It's uniform and it points down. Okay, so here's my electric field. And let's say now I have a ball here, but let's say that it's carrying some charge. Let's say it's carrying a positive charge, positive Q0. Okay, so it's a positive charge. Now, if I release that charge in this electric field, it's going to fall in exactly the same way the block did, right? Because it's going to experience a downward force, right? Again, free body diagram. If this is my charge, it's going to feel a downward force that's in that direction, right? And that's going to not be F sub g, but that's going to be F sub e, right? Which is going to be Q times E. So you can see this is completely analogous to mg in the gravitational world, right? Gravity acts on masses. Electric fields act on charges, right? But the idea is very similar. And so if I release it from this initial position A, and I allow it to descend to some final position B through some vertical displacement, which I'll call delta S, to be consistent with your book, then again, we can calculate the work done by the electric force. In this case, F sub E, and the displacement is delta S, and the angle between the displacement, which is down, and the electric force, which is also down, is again 0 degrees. So you can see this is completely analogous to what I was doing before. And since F sub E is Q times E, in this case Q0 times E, I can multiply that by delta S, and I've got the work done by the electric force over the course of this journey. So you can probably see what's coming if I then define some electric potential energy such that the work done by the electric force is equal to the negative of the change in the potential energy of the charge, then I can do the same sorts of games that I did in Physics 1. This is going to be my definition. This is going to be how I define electric potential energy, whereas this is analogous to mgh, right? mgh, or this formula is not always going to necessarily be. This formula works in a situation where we have a uniform electric field, which may not always be true. So I'm hesitant to define use of E to be something as general as this. But you can see in this situation at any rate that as it descends from point A to point B, the work done by the electric field is positive, which means the change in potential energy is negative. And that should make sense too, because if I place the object at position A and let go, then what's it going to do? It's going to pick up speed, it's going to acquire kinetic energy, and so it must be losing electric potential energy. So that is electric potential energy. What is this electric potential? Well, I'm going to define it. It's actually similar to the way we're going to define it in a similar way that we defined electric field. If you recall, the definition for electric field was F sub E divided by Q0. So we divided the electric force that a test charge feels divided by the magnitude of the test charge, and that's how we defined electric field. In a similar way, we're going to define a new quantity here called electric potential, right? So in this case, a charge will undergo a change in electric potential if it undergoes a change in electric potential energy. So delta UE. So that is if a charge either gains or loses electric potential energy, right? It either moves up or down in an electric field, right? Then it will also undergo a change in potential. And the way we find delta V is we divide delta U by Q0, right? This must mean that it's also related to the work done by the electric force, negative WE is divided by Q0. So right away we can actually see what the units of this new quantity would be. It would be work is measured in joules, charge is measured in coulombs, so electric potential is measured in joules per coulomb. In fact, we have a name for that. We call 1 joule per coulomb a volt. I in particular shorthand a volt as a V with wings, right? I want to avoid absurdities like V equals 10 V, right? Potential equals 10 volts. I want to distinguish between the unit of the thing and the thing itself, just so you know what I'm doing there with the wings. Okay, so that is, now I mean, volts, that's something you've probably heard before, 120 volts, right? A 9-volt battery, things like that, right? You've heard this unit before, right? But you probably haven't really thought of it in terms of potential energy before, right? This is the new physics approach to this perhaps somewhat familiar concept. So we need to try and figure out what this all means. And I think the best way to do that is to just start with an example and just see how it works. Okay? Okay, so my example is going to be like this. Let's say I have a battery. So here's like a D-cell battery or something like that. Let's say it's a big battery, maybe like a car battery. Let's say it's rated at 15 volts. Right? And let's say, so this would be the positive terminal of my battery, this would be the negative terminal of my battery. And let's say I have a wire connected from the positive terminal of my battery to a plate, a metal plate, and from the negative terminal of my battery, I'm connecting it to another plate. Now, the 15 volts must mean that the potential, the electric potential at the positive terminal is 15 volts higher than at the bottom, at the negative terminal, right? And so what's going to happen then is the battery is going to make the top plate positively charged and the bottom plate negatively charged. That's the job of a battery, to move charges around, and in this case what it's doing, it's taking electrons from the top plate and placing them on the bottom plate. Okay? And that's going to be setting up an electric field that's going to point from the top plate to the bottom plate. Right? So here's an electric field. Potential. We know that the potential, let's call this plate A, let's call this plate B. We know that the potential at plate A, let's call it 15 volts, and the potential at plate B, let's call that 0 volts. Now, it turns out that's kind of an arbitrary decision. You remember how when you were talking about gravitational potential energy, you could set the 0 of potential energy anywhere you like. You could set it to be the ground. You could set it to be somewhere up here. That's sort of your choice. It's an arbitrary choice. It's kind of similar with electric potential and electric potential energy. The 0 that you choose, or the location where the potential is 0, is your choice. I could, for example, this being a 15-volt battery, I could just as well say that V sub B is negative 15 volts and V sub A is 0. That's my choice, right? The important thing is that plate A, is 15 volts higher than VB. That's all this means, right? When you're talking about potentials, it's delta V's that are important, not absolute V's, okay? More on that later, too. Okay, so here is the scenario. Now, there's lots of different ways. Some of the language you may be hearing in the next couple days and weeks are things like, there's a potential difference between plate A and B. There's a 15-volt potential difference. The potential difference between plates A and B would be what I would call V sub AB. That's defined as VA minus VB, which in this case is positive 15 volts, right? I could also, for example, say that there's a potential drop as you go from plate A to plate B of 15 volts because it goes from 15 down to 0, right? So this is just all the types of things that you might be hearing. Let's take a charge, a positive charge, and move it from the top plate to the bottom plate. Okay, so let's say that a charge Q0 positive moves from A to B. Right? What is the change in potential of the charge? Well, delta V for the charge would be V final. Since it ends up here, that would be VB minus V initial, which is VA, right? Which is negative 15 volts. So if a charge goes from A to B, then it experiences a change in potential of negative 15 volts. Notice that that's completely independent of the charge, right? It's independent of Q0. It doesn't matter if it's 1 Coulomb or 300 coulombs. Delta V in this scenario is going to be negative 15 volts. It's a different question if I ask about the change in potential energy. Right? Because delta U, the change in potential energy, would be Q times delta V. So for example, if this were a proton, then delta U would be E, 1.6 times 10 to the minus 19 coulombs, times negative 15 volts, which is 2.4 times 10 to the minus 18 joules, right? So whereas the change in the potential as it went from A to B did not depend on the charge, the change in the potential energy does, right? So in much the same way that the electric field is kind of like a hypothetical force, electric potential is something like a hypothetical energy. If you put a charge at some location, then it's going to have a certain amount of energy. But if there's no charge there can still be an electric potential. Okay, now as you can see, it's kind of important to keep your signs straight, so I want to go through this one more time. Let's go back to our scenario, just the same scenario that we just had. We're in some region where the electric field points down, right? And let's say that a charge moves from, say, position A to position B. Already what you saw, like in the previous example, the electric field between the plates pointed down. A, which was the top plate, was at a higher potential than the bottom plate. So this was at a high potential. And this was at a low potential. Right? Potential is just a property of the space where you are. And if I were to take a positive charge and move it through this displacement from high V to low V through some displacement delta S, then we can ask the question, what happens to V, what happens to U, and what is the sign of the work done by the electric force? So my question to you is, as the positive charge goes through this displacement in this downward electric field, what happens to V? Does it increase or decrease? What happens to U? Does it increase or decrease? And did the electric force, do positive or negative work? Pause for a second and think about that. Okay? As you go from here to here, you're going from high V to low V, so potential in this case decreases. So potential decreases. Since U, potential energy, is just Q times delta V, and if this is a positive charge, if V decreases, then U is also going to decrease. And that should make sense again because, again, I can release a positive charge from up here and it'll go down and acquire kinetic energy. So it must come at the expense of potential energy. Now, what about the sign of the of the work done by the electric force? In this case, the electric force points down because it's positive charge in a downward electric field, and so the force is in the same direction as the displacement, and so the electric force does positive work. That's also consistent with W sub E equals negative U E. U sub E. If delta U is negative, then Fe is positive. Now, let's imagine another scenario. Let's say I do the same thing, but with a negative charge. Okay? Same thing, but with a negative charge. I take this negative charge and I move it down through the same displacement delta S. Now, that's not going to happen on its own. I could put a positive charge here, release it, and it'll fall because the force is down. In this scenario, if I put this negative charge here and release it, it's not going to want to go down because it's a negative charge. It's going to feel a force that's up. So if I were to release it, it would move up. So in order to make this negative charge go through this displacement, I'm going to have to push down, right? That's okay, I can do that. But just bear that in mind when I'm talking about this. In order to get that negative charge to move down in this electric field, there's going to have to be another force, an applied force. Now, what about the sign? What happens to V? What happens to U? And what about the sign of the work done by the electric force in this scenario? Pause and think about that. In this case, V, remember, V is just a property of space. If we go from high to low, then V naturally decreases. Okay? It's independent of the charge. If I go from A to B, regardless of what the charge is, V is going to decrease because up top is high, down low is low potential. What happens to U? Well, now in this case, the potential energy, since delta U is Q times delta V, and Q is negative, in this case, U is going to increase. So you can see that U is dependent on the charge, does depend on the charge. And that makes sense too, because if I push this thing down and then release it, what's it going to do? It's going to fly right back up. And so in this case, F sub E, since delta U is positive, F sub E must do negative work. But that should also make sense because as I push this thing down, there's an upward electric force that's in the opposite direction as the displacement. So the electric force is up, the displacement is down, so that cosine 180 gives us a minus sign, and the work done by the electric force is going to be negative, right? So I say all of this because it's important to keep these signs straight. This can be a conceptually tricky thing. So keep that in mind as we move forward this week.